Thank you. So our final talk for the workshop is by Mohammad, and he's going to talk about black box operations in a quantum world. You're on. Thank you.
Thank you so much. Thank you, organizers, for such a great workshop. And sorry that I cannot be there in person. I'm going to talk about black box separations in a quantum world. The title is a tiny bit different from what was posted, but it's pretty close. And I'm going to focus on results that are from a crypto paper from the last crypto with co-authors Per, Kaimin, Hao, Xiwan, Yaoting, and myself. And yeah, so let's get started. Just to check, do you see like the Zoom things on the screen? I guess it's fine. Okay, nothing that you shouldn't see. Okay, perfect. So let's go over some basics. I know everyone there knows them. In part, I prepared them because I guess some others might see the talk, but I hope you don't mind me go over some basics. You know, we have assumptions in cryptography, of course, and the reason that we have them is that P different from NP seems to be, it is necessary for most of the interesting things in crypto. We don't know how to prove it. Therefore, we have assumptions. Ideally, we want to assume just P different from NP. Even that we cannot do. We make stronger assumptions and we are fine with it. And, you know, we have panels like yesterday who discuss what assumptions are better. And here are some properties that are typically considered good. Having a generic assumption that is, for example, one-way function as opposed to factoring, that we can have a family of implementations for it. That's a preferred thing. If it's falsifiable, if it's well studied, and maybe inspired by physics, something that is simple to state is also good to have. So we make such assumptions, and then we do construct the primitive that we want to construct, and then we give a proof of security. So that's how we do business in cryptography. And there are two major tasks. I mean, there are more than these two, but those two classical questions in cryptography are secret key encryption and public key encryption. For secret key encryption, the situation is pretty good when it comes to assumptions. In particular, we know how to use one-way function to do essentially everything we want to do, and that is in fact minimal. Till we actually prove them to exist, then that's a different story. But so far, this is a minimal assumption. But when it comes to public key cryptography, the situation is really not good. For authentication, it's fine. Signatures, we can base them on one-way functions. We pay an efficiency cost. That's kind of okay from an assumptions perspective. But when it comes to public key encryption, the situation is really bad. It's more like an art of picking the right structured assumption, like LW or DDH or something else. And there is a survey advertising by my advisor, so you can look at it to see some of them. It's a great survey. So what is the big question? Can we base public key cryptography, in particular public key encryption, on one-way functions? And that's open. We still don't know how to solve it. And it's been a while. So what do we do? Maybe we can cry or go home, but not all of us did that. So Impagliazzo and Riduch in '89 explained to a large extent why we have failed. They showed that at least for a construction that is so-called black box, there is no way of getting there from one-way function to public encryption. And let me just say quickly what a black box construction is. That's basically the only definition of black box construction that I will have in this talk. It is going to be a construction that uses a generic assumption and uses it as a oracle in the implementation. So we use the one-way function. We don't care how it's implemented. We use it as an oracle. And in the proof of security, we also treat everything as a black box whenever we can, like the implementation of the one-way function again, or the generic assumption will be used as a black box. The adversary will be also used as a black box. And black box constructions relativize. They have some nice properties. In addition to relativizing, they have some properties that are practically relevant. They are typically more efficient. They compose better. If we don't really look at the code of the adversary, you might plug in something that is not really a circuit there. potentially, if you don't reset it, you might plug in like a quantum solver or a human brain. So they're better for many ways. Therefore, if you make a non-black box construction, black box typically it's considered interesting, but when we don't even know how to do something, they're of course even more interesting. So it's a very influential line of work initiated by the Impagliazzo and Riduch paper. Now, today's theme of the talks, of course, were about quantum, and of course, I'm going to get into that. So in a quantum world, cryptography is changing. You see the number of papers going up and up every conference. So it's now an elephant in the room that more and more people actually do talk about. But how does it affect cryptography technically? It really depends on which angle you look at it. There are kind of good sides and bad sides in sense. So adversary could be quantum. So that's not the great news because we have to update our protocols and make them quantum safe or post-quantum. But it's also the case that honest parties could be quantum. So they could implement things in a quantum way that we couldn't do before. So that brings up new avenues that could be like a smiley face now. And of course, we are going to revisit everything in light of having quantum power and quantum communication. How does that affect reductions and separations? Typically, how it works is that we pick your favorite reduction or separation. I have the separation in red because that's what I'm typically more interested in or naturally attracted to. So you pick your favorite reduction or separation, then you need to extend the definition of the primitives that are involved somehow to the quantum setting. So the pick that you had in the first line maybe was from the classical setting, and then you need to think about what it means to have something like that in the quantum setting. So the primitives involved should be extended to the quantum setting, and then we revisit whether the reduction or the separation holds. And this extension of the primitive to the quantum setting, I would say it comes in many flavors, but I think you can think about it in several hierarchies that I think all are very interesting in their own. So the most basic extension of a primitive to the quantum setting is that you just keep everything classical in terms of the implementation, the input output, and you only give quantum power to the adversary. So that's the post-quantum or quantum safe setting. But this is kind of mechanical. So you don't really need to define something from scratch. Usually the post-quantum definition is natural. You can make it kind of a mechanical process as well. But one step going further, you can take the primitive that existed and now keep every communication classical, inputs classical, but give quantum computation to the processes that go from those inputs to the outputs. And that's going to be more relevant for the focus of the talk. For example, we can have a key agreement protocol in which the messages are classical, but the parties, Alice and Bob, are not classical anymore, and they're quantum powered. And the third is that, we go really beyond the limitation of even keeping the messages classical, and that goes to a lot of topics that were the subject of talks today. You can think about commitments or many other primitives in which now even the communication is classical, which means that, of course, all the parties will be, the communication even is quantum, which means that even parties will be quantum powered as well. So I really want to emphasize that there is a merit in every level of going quantum here and revisiting the questions. Of course, going all the way to quantum is interesting, but it's also good to keep in mind that, the internet is not going to become quantum tomorrow, and it's not clear how long it takes. Maybe we will get local quantum computing really faster than having really full-fledged quantum communication as well. So the questions in the middle are also interesting. So what is known about the separation side in the quantum world? It's not a survey, but I'm listing some of the works that I think are interesting or I'm aware of. So the work that really started this line of work is the work by Hoso Yamada and Yamakawa from Asia Crypt 2020, the best paper of that year, in which they showed that if you revisit the relation between collision resistant hash functions and trapdoor permutations, for which we know a classical black box separation by Simon and a generalization to the chapter permutation by Heitner et al., you can prove a similar black box separation when you allow the implementation of those primitives to be quantum, but you keep every kind of input-output classical still. So they defined what it means to have a quantum black box reduction, and they proved their separation. And there are also results that showing that when we have quantum messages, things could be even more surprising and maybe more interesting technically. In particular, pseudo-random states do not imply one-way functions in a black box way. This is the Kretschmer's result, but they do imply non-interactive commitments in a black box way from the two papers appearing in Crypto, last Crypto. So, you know, I don't have to repeat. So one-way functions are not, of course, necessary for quantum non-interactive commitments. But there is also a paper from just the last Eurocrypt presented a few days ago that showing that if you actually emphasize on having classical messages in your non-interactive commitment, there is evidence that black box constructions from one-way functions, so it's incomparable to the, you can separate it officially from one-way functions and show that some previously known separations by myself and Raphael extend to this setting as well. There are not many other papers around, so black box separations in a quantum world is kind of like a Wild West, so you can find many basic questions that are still open and interesting to look into. And my favorite one that I'm going to focus for the rest of the talk is going to be about the question that I started the talk with. Namely, what's the relation between key agreement and one-way functions when we move to the quantum world? By the way, I'm not really sure how I would hear the questions. So if you said something, I hear you well. So if there was a question, I guess.
You'll hear. Yeah, we'll just speak up. So whoever has a question, will speak up, so you'll hear us.
Thank you. So of course, stop me at any time if you had any question. So this is the main question of the talk. So what is known about it? What's the relation between them? Of course, if you allow quantum communication as well, then the answer is known. So BB84 tells us that we can have a statistically secure key agreement if you have quantum communication. And if you are also really emphasizing on public key encryption, and you know we are okay to make one-way function as an assumption, there is a recent series of works that show you can actually just assume one-way function and get public encryption if your public key is somehow a quantum state with some carefully stated properties of how many copies you need to have, or whether it's can be tampered with or not. But essentially, there are positive results that state that you can have something like that if you, as I said, allow quantum communication, in particular if your public key is quantum. But it doesn't answer the question that I want to focus, which is the question of getting key agreement using classical communication and quantum computation. Is it possible to do it from one-way functions or symmetric key cryptography? We still don't know. And the question was first formally stated, at least in public arena, by this in the same paper that initiated black box separations in the quantum setting, the Ajaker paper. The initial versions of the paper, I think, even mentioned this question, even though I think many people maybe have heard about it before, but this was for the first time stated officially. And in this talk, I'm going to give some partial negative answers to the question, and hopefully you will be motivated to at least take on some of these, or maybe go all the way and solve the full-fledged version of the question. And that's going to be the rest of the talk. So what is the outline for the rest of the talk? I'm going to define the problem formally, a little bit more formally, then state what is our conditional partial impossibility result. We will see some details of the attack, and also I will explain the condition under which we prove the results, which is a conjecture, why we make it, what is it, and how is it justified, and wrapping up with some questions. So I'm going to focus on key agreement from a random oracle rather than a one-way function or hash function, which is not surprising. We use random oracle for proving possibilities or impossibilities. So let's first define this formally, and then we will see why is it okay to work with this model, even if you want to really study, say, something like one-way function. So if Alice and Bob have access to a random oracle, it means that they have access to this function h, which is a huge, gigantic Boolean function. For simplicity, let's say it's Boolean. The capital N here is something like 2 to the security parameter. So think about like 2 to the D. I use D for the security parameter, which is a little bit non-standard in this talk, but I think because it has to do with degree of something, that's why I chose it. So this is like 2 to the D. So it's a huge table, random table, and they have a random access to this table. They each ask up to D queries to this oracle. I'm talking about, say, classical setting now. So they each ask D queries to this oracle, and they, of course, can interact back and forth. And at the end, they output the key, each of them. The keys should be the same. And the security says that an eavesdropper who looks at the exchange messages and asks a polynomial number of queries over D cannot really guess the key better than a random guess up to a negligible advantage. So this is what key agreement in a random oracle model is defined, what it is, if we could do it. Why do we care about it in the random oracle model? If we can show how to do it in the random oracle model, the practitioners don't really care whether you make it one-way function. I guess they just plug in their favorite hash function and they have a great key agreement protocol that would likely be secure even if you break all these beautiful structured problems like LWE or DDH. So that would be really fantastic, but not P equal to NP, of course. But if it's not possible, and if you can rule out the key agreement from a random oracle by breaking it with a polynomial number of queries, regardless of the efficiency of the attack, it still rules out a possibility of basing your primitive on one-way functions or hash functions, collision-resistant hash functions in a black box way. So it's a win-win study. The both sides are interesting. Of course, the first one would be more interesting, but it might be not the case. So is it now possible to get really key agreement from random oracles? Of course, the classical results of Impagliazzo and Riduch showed that you cannot do it. And further quantitative improvements showed that you can make the attack even quadratic over the number of queries of Alice and Bob if everything is classical. And because Merkel already had a protocol that was quadratically secure, we know the tightness, we know that the result is tight. So it's kind of solved for the classical case, but we are interested to know what happens if Alice and Bob can now have quantum computation while they stick to their classical communication. And if we say they are allowed to have quantum computation, we have to also allow them quantum access to this oracle. Eventually, that oracle will be a hash function, and it can be implemented in like a polynomial size circuit, and then whoever has quantum power can indeed run it in quantum superposition. So even though it's a random oracle, it will not be polynomial size. We still have to extend our model and allow quantum parties to call it in quantum superposition. So how do we do that? Well, accessing oracles in quantum superposition is something that is defined and is well known even beyond random oracles, but for the random oracles case, it was popularized by the Bonnet et al. Paper. So it simply means that we have this random oracle, which is our hash function. If it was a classical query X, we could ask it and the oracle would give us the answer. What is a quantum version of this? I'm not going to define it, but roughly speaking, it means that you will have registers for your query and your answers. And when you ask like basis questions or that are exactly matching these classical queries, you will have clearly defined answers, and the quantum algorithm can ask a linear combination of those queries with complex coefficients, and we'll get a linear combination of the answers with the same coefficients. And they can, of course, do measurements and do all that. But the queries are going to be quantum, so they can be superposition queries to the random oracle. So that's what Alice and Bob can do. And what is known in this setting. So the setting is that everybody can access the oracle in quantum superposition, the random oracle, and we stick to classical communication. What is known before? There are, in fact, some interesting results known, some observations and some technically challenging results that are more like fine-grained flavor. So first of all, let's remember that the Merkle puzzle protocol completely breaks down because the classical Eve in that protocol has to find one point among d-squared points. That's how we get d-squared security. But using Grover search, you can exactly solve it in a linear number of queries over D. So order of the queries will be enough. But is that the end of the story? No. In fact, there are ways to make this super linear secure and get back some non-trivial security. First, it was observed by Biham Gordon and Ishai, yes. And concurrent work also showed that you can do it, and that concurrent work eventually turned into a crypto paper that showed you can pretty much get to quadratic security if you give Alice and Bob quantum access to the random oracle, and it still needs quadratic over D number of queries, even if it can ask the oracle in superposition. These are interesting starting points in some sense, going back to where we were in the classical setting, but it was left open whether any polyquery attack can always be obtained when we have a arbitrary protocol. And that's exactly the question we have. So what do we prove? So our main result is the following. The main result is that assuming what I would call a believable conjecture, the objective part is that is conjecture, about low degree polynomials that I will talk about, one can break any D-query quantum key agreement protocol with classical. I won't repeat that it's a classical communication all the time. It's going to be classical communication. But I emphasize that the protocol needs to have perfect completeness. Then you can break it with polynomial number of queries. So I'm going to say a few words about everything that I am emphasizing on this theorem. But before that, let me say that there are also other results that we prove, and I'm not going to focus on. We show that if only one of the parties is classical, you don't need the conjecture. So you can prove it unconditionally. Unfortunately, you still need to assume perfect completeness. And finally, we kind of justify this conjecture by showing that some form of conjecture seems to be necessary for such a impossibility result. If you want to break your protocol classically, in fact, we break the key agreement only with classical queries. So the attack that we give doesn't really use the fact, it doesn't really leverage quantum power. It only asks classical queries. And as long as you are limiting yourself to such attacks, you are going to be stuck in some unproven conjectures. Namely, there are unproven conjectures that depend on which way they are going to be resolved. You might end up having a positive result that is secure against classical queries attacks. So I'm going to talk about them also a little bit towards the end. But let me go now over some grievances. So this is the theorem. And what is annoying about this theorem? There are a few things that I can point out. So the annoying point first is that it's assuming perfectly complete protocol. Why is it not a great thing? We even don't know how to achieve superlinear security for a key agreement in the classical setting from a random oracle. So if you emphasize on perfectly secure protocols, Merkel's protocol actually doesn't work for a random oracle. And it seems like you can make it perfectly complete by like hashing things and so on, but it doesn't really work. And if I may, I even conjecture that it's not going to work. I don't know how to prove it though. It's I think Boaz said it's a sour question once. He might not even remember, but I looked into this question years ago, and it's one of those questions that if you prove it, it might not be really interesting for anyone, but you might be stuck with it for years. So I think it's impossible, but I don't know how to prove it. So that's an annoying thing. Another thing is that if you assume perfectly complete protocols, if you assume perfect completeness, there is in fact a much simpler proof of impossibility by Brakersky et al. You don't need really the full-fledged Impagliazzo and Riduch machinery for that. But in the quantum setting, we still are stuck at this perfect completeness. The attack itself is classical. You might say it's a plus, but eventually it's an issue because we know that the classical attacks are going to be stuck somewhere because of the barriers that I mentioned. And finally, there is really no reason so far that I'm aware of that makes a justification that the conjecture that we make is really hard, because the conjecture that we make might as well be easy and the perfect completeness case might be easy. That's actually what I feel. I think the conjecture is solvable as opposed to some similar but different conjectures have the same flavor. Okay, so let me go into a little bit of technicalities before end of the talk. So some details of the attack and some parts of it that might be useful even if you don't really like the theorem or results of this type. So let me first recall how the key agreement in the classical setting can be broken in the random oracle model with the style of the proof of the paper with Boas. It's based on something we call epsilon heavy queries that is very simple to define. So what is the attack? The attack says Eve asks every query that is quote unquote epsilon heavy from the oracle. What is an epsilon heavy query? Epsilon heavy means that Alice or Bob have a chance of at least epsilon asking it from the oracle, conditioned on everything that Eve knows so far. So originally Eve only knows the transcript, but after it gradually gathers information about the oracle, it's the probability distribution of Alice and Bob's views in eyes of Eve can evolve. And at every moment, if something has epsilon chance of being asked by Alice and Bob, it's a heavy query that Eve can go ahead and ask. And when there is no such heavy query left to be asked, Eve just simply outputs the more likely key. So that's the attack that would work. This is not exactly how the attack of the paper is written, but if once you prove the more complicated attacks of the paper to work, then you can also derive that this simpler attack actually works. So the analysis says that, because everything that you ask had epsilon chance, you can prove by linearity of expectation that there are not going to be too many of them. The interesting thing really is to show that this is enough information to find the key. And that's much harder. But now that we have this attack, at least can we define a quantum version of it? So can we extend this epsilon heavy query attacker to the quantum setting? That should be doable. So let's see what we can do. It's not as clear as it might feel that it should be. And the reason is that in the quantum setting, the queries are not really intuitive like the classical setting. So the queries don't really coexist. And it's not clear how to define a quantum epsilon heavy in a really quantum way. And even if you ask a quantum question from the oracle, you will have a challenge of whether you should really read the answer or not read the answer, because if you read the answer, if you make measurements, you might get trouble down the road. So there was a lot of things that would make life easier when we had a classical oracle, because we just write down the probability distribution, see what query is more likely to be asked, and we ask it. And I want to say that, in fact, there is a way to generalize it. So I'm going to now show you how to generalize the epsilon heavy query definition to the quantum setting. At least we will have an attack, candidate attack. How can we define an epsilon heavy query when Alice and Bob's queries are quantum? So the intuition is the following. Classically, if a query is not asked, its answer remains uniformly random. So think about the distribution of the answer of a query. Once you ask that query, the distribution is no longer uniform. You know the answer. But before you ask it, it's uniformly random. And before even Alice and Bob ask a query from the oracle, it is going to be uniformly random. But if Alice and Bob can ask quantum queries, of course, even a single query can touch everything. Even a single query can have non-zero coefficients for every classical query. So that's going to be kind of making issues if we really want to ask queries that are really asked from the oracle or not asked from the oracle, because everything can be asked to some extent. So everything can be kind of asked in a fuzzy way. And that makes things a little bit challenging. So what do? We use ideas from the compressed Oracle machinery of Gendry, and we don't really use the full-fledged version, but some of the ideas are really useful, and we can use them to extend the epsilon heavy notion to the quantum setting. So what is the message, one message from that line of work? It says you can choose to purify your oracle, and then you can choose your view of the oracle to be interpreted in a different basis than the computational basis. You can look at the answers in the other bases. In particular, you can look at them in the Fourier basis. And here the Fourier basis will be just the Fourier over Z2, because the oracle is binary. For each query, the answers distribution, you can write it in Fourier basis. And if a query is not asked, it's still uniform. It means that in the Fourier basis, it's 0 of the Fourier basis, the answer distribution of that point. And you can use that to define what it means to be epsilon heavy by defining it informally as follows. It means that if you measure the answer to that query, it's a classical query. So if you measure the answer to that query in the Fourier basis, what's the chance of getting 0 versus non-zero? If the chance of getting non-zero is more than epsilon, then it means that the answer, and I'm not being formal about what is even the quantum state here. This is going to be a quantum state of everybody involved, Alice, Bob, and the oracle. But if you really just focus on the oracle and purify it and have a quantum state that captures the situation of the oracle at a particular moment, the epsilon heaviness, according to this definition, says that you have at least epsilon chance of getting non-zero answer if you measure that answer in the Fourier basis. So originally everything is zero. But once you make queries to the oracle, the oracle's state will evolve, and therefore some of the points might start to have a answer distribution that gets away from the uniform. And this is kind of a necessary condition to be read. So a sufficient condition to be read. So if an answer to a point is away from 0 in the Fourier basis, it means that in fact it is touched. So one of the parties has really asked that query, and that's why the answer has been kind of away from 0. So this is the informal definition. You can also see the formal definition in the paper. I'm going to kind of show it to you, but not really get into the details. The way you should really think about it is that if you have a quantum state that captures the oracle in the purified way, every point that is heavy is defined by saying, look, I ask that point from the oracle, and this is a classical point. This is a classical query. If the answer is non-zero in the Fourier basis with more than epsilon chance, it is going to be called epsilon heavy. So one comment that this definition is kind of kosher in the sense that it does in fact generalize the epsilon heavy definition from it has some useful properties. Even if your original algorithm was classical, you can show that there are some relations between them. I don't emphasize on it. This is not equivalent, but it does work also in the if your original algorithm was classical. Now, quantum epsilon heavy attack, you can really write an attack immediately based on the definition of quantum epsilon heavy queries and ask, is this attack going to work or not? So this is the same exact as the classical attack. I just changed it to say that the Eve attacker is now asking quantum epsilon heavy queries from the oracle whenever they exist. As long as they exist, it keeps asking them. And when there are no more epsilon heavy queries left in the quantum flavor, you just output the more likely key. So efficiency of the attack is the same as before. You can show that linearity of expectation guarantees that you will not really ask too many queries from the oracle. The interesting thing, again, is to show that this is enough information for Eve to really guess the key. Is this really all Eve needs? And if you really emphasize on your attack to be classical, intuitively, this is actually the best you can do, because if something is epsilon heavy, it means that you will go ahead and ask it. And if it's not being asked by Alice and Bob, you already know what the answer will be. It's going to be uniform in the classical case. So it is really natural to conjecture that for classical attacks, this is the best you can do. So
can I ask a question?
How can we analyze? Yes.
How does Eve know what are the epsilon heavy queries? I mean, I'm not sure that I understand the setting. Is it like Eve is like analyzing Alice and Bob and makes queries to the real oracle.
To the real oracle. Yes. So let me give you a little bit more details. I simplify things maybe too much. So suppose you're Eve, and in your view, you will purify everything. So you assume that oracle is purified, and then you look at the transcript. Condition on knowing the transcript, you will imagine what would be the state of Alice and Bob and oracle. Alice registers, Bob registers, and oracle registers. And now you can judge, with respect to that specific quantum state, you can judge each and every classical queries to the oracle to be epsilon heavy or not. Okay. Epsilon heavy means that if you read that query in Fourier basis and measure the answer, it will be non-zero with probability at least.
I can even analyze it completely off. It doesn't even need to be anything quantum here, right? I could just sort of write it on paper if I have like exponential.
Indeed. Yeah, it's information theoretic, so you don't need any quantum, because I'm not putting any bound on Eve's computing power.
Sure.
So you can do everything in your head, and then
power. It's about what you have access to. Okay, sure.
Yeah, the access is classical too. Yes. So it's really important that this is a classical attack. That's why it might be limited too much. And so the attack, you can think about it to be essentially the same attack, but just modifying this heaviness to be quantum heaviness. And how do we analyze it intuitively? How this conjecture shows up that I told you about. If you want to analyze this attack, at the very high level, this is what's happening. You keep asking the heavy queries from the oracle, and at some point, there is no heavy query left, but you haven't found the key. So suppose the attack fails, because if the attack succeeds, we are happy. But if the attack fails, we want to get a contradiction somehow. So if the attack fails, it means that in eyes of Eve, the key is still 50-50. So you can think about the quantum state of Alice and Bob and oracle, and you see that if I measure the corresponding register of Alice that outputs the key, it's 50-50. So I can really kind of, informally speaking, I can condition on that bit being 0 or condition on that being 1. More formally, I have to trace the state to get two different states that correspond to the world that key is 0 or that key is 1. So in eyes of Eve, I will have two quantum states that have the following properties. Both of these quantum states will still have no heavy query left. Originally, there was no epsilon heavy queries, but because the keys were 50-50, I'm essentially, like informally speaking, I'm conditioning on an event of 2, which means Q 0 or, sorry, half, event of size half. It blows up every probability at most by factor 2. So everything that was at most epsilon heavy is now 2 at most, 2 epsilon heavy. So still there is no heavy query left. This can be shown to translate into having small influence of the variables in a polynomial that you can write to represent the state of the quantum of the oracle. More formally, it's not going to be one polynomial. It's going to be a distribution over polynomials after you kind of measure Alice and Bob's registers. But I'm not going to say how exactly this translates to a polynomial, but there is going to be another condition that this quantum state has, because Alice and Bob are asking at most D queries. This also translates to something that can be formalized into a degree of a polynomial that captures the state of the oracle. And the conjecture that we have states that if you have two such quantum states that can be rewritten as polynomials, as long as they have low influence and low degree, they can be combined into one oracle that is both compatible with Alice outputting 0 and Alice and Bob outputting 1. So you have two quantum states. You can combine them to have the same oracle, but in one of them, Alice is outputting 0, and in that quantum state, Alice is outputting 0, Bob is outputting 1. So that would violate the perfect completeness condition. So what is this polynomial compatibility conjecture? I'm going to tell you formally. It's very simple to state. But just the informal part of the analysis is that the conjecture is exactly trying to capture what the contradiction you want to get, and it exactly says that if you have two quantum states that have low degree and low influence, they can be combined into a quantum state that violates perfect completeness. But what is the polynomial compatibility conjecture? I can define it in two. I can define it in I can give you the definitions in one slide and the conjecture in the next slide. So I'm going to define very basic things. So suppose I have a polynomial here that is over +1 over variables who eventually get +1 or -1. So without loss of generality, it's a multilinear polynomial. And the number of variables is huge, is the number of points, queries you can classically ask to the oracle. Think about the polynomial of this form. The degree will be, the degree of this polynomial is just the maximum monomial's number of variables. What is the L2 norm of this? The norm of the variable is like, give it a random input and take the square value of it. That's what L2 norm is. We want to normalize it if it's supposed to reflect, for example, a quantum state. And the influence of each of these variables can be defined in many equivalent ways. If you have already seen a definition of influence of variable, that's going to be exactly equivalent to this. But if you haven't, it just means look at all the monomials that have that variable and sum their coefficients. So it means like how much kind of monomials that have that variable have a weight. So we have influence degree, and suppose we normalize such a polynomial all the time. So what is the polynomial compatibility conjecture? It simply says, suppose you have two polynomials, multilinear polynomials over these large number of variables, exponentially large number of variables, and suppose their degree is bounded. So their degree is bounded by D, and I don't have a lot of time, so I need to plan, but I think 3 minutes should be enough. So suppose the degrees are bounded by D, and suppose they both have the same unit norm, and more importantly, their influence is bounded. So the degrees are bounded, the influences are bounded. How small are the influence of each variable? Think about the influences being sufficiently small in terms of a polynomial over D, but even 1/10D is still believable. At least I personally believe it to be work. But if you prove it with 1/D squared or 1/D to the 10 or 1/D to the 100, that's going to be enough. The conjecture says that if you have two polynomials of low degree and low influence, their multiplication is non-zero. That's it. So there is going to be an input that they're both non-zero.
A quick question.
Yes, yes.
Have you considered Hunda theorems for this?
Which theorem?
Hunda theorems. They have the exact Hunda theorems. They have very low influence and they will touch a very few variables.
Yeah.
The output is forced to be Boolean.
I'm pretty sure we have looked at them, but I can discuss with you later what are the differences. There are some theorems that are closer than Hunda theorems, like the invariance principle type theorems that are even closer, and they can give you proofs of this for exponentially small influence. And we prove this conjecture for some range of parameters. So in particular, we can prove it. So one evidence that is true is that we can prove it for the case that the influences are exponentially small. As I told you originally, kind of proofs were complicated, but you can show a proof based on basically careful applications of Cauchy-Schwarz. But exponentially small influences would make the conjecture correct, but we want it really for polynomially small. So if you are okay with exponentially many queries in breaking key agreement, probably you will not be. But this is going to be unconditional for perfectly complete protocols. Even that doesn't seem trivial. So if you want to break a quantum protocol with exponentially many classical queries, this is like 2 to the D, and D could be like 10, and 2 to the D is not really huge. It's independent of the number of queries of the oracle. So that is still, in my view, not trivial, but it's more like the support for the conjecture. So what else do we know to be about the conjecture? As I said, it seems to be potentially true even for influences like 1/10D. Maybe that's too ambitious, but that seems to be compatible. And my favorite reason for it is that our Fourier expert actually believes it eventually. He didn't seem to believe it at first, but a co-author pair and now thinks it's correct. And I want to wrap up the talk. So let me just tell you that, as I said, the conjecture that we have somehow is necessary if you want to emphasize on classical nature of the attack. So there is this conjecture by Aronson and unbiased, that if the conjecture is false, you can actually get a positive result that is secure against classical query attacks. So I'm not going to define the simulation conjecture, but roughly speaking says that in the random oracle model, if you have a quantum algorithm that makes the queries and outputs a bit, for most of the oracles, you can approximate that probability arbitrarily closely by asking only classical queries to the oracle. So if you emphasize on the algorithm, quantum algorithm really being a total function, this is not a conjecture anymore. It's a well-known theorem that the query complexity of quantum and classical are polynomially related. But this simulation conjecture is that, I don't have a total function. I arbitrarily output 0, 1 by querying the quantum oracle quantumly. And the conjecture says you can still approximate that probability for most of the oracles classically with polynomial number of queries. It's open. It's a well looked at conjecture. If it's false, you can get a positive result. So what does it mean? It means that we have to probably look at quantum queries to really attack similar to Impagliazzo and Riduch. So let me wrap up basically with the questions. I hope you will be interested into looking at this polynomial compatibility conjecture based on the criteria of the panel yesterday. I think it's an interesting thing. It has both like a mathematical simplicity and implications that motivate you. Most important question probably, can you define a quantum attack that really goes outside this framework and then therefore breaks things unconditionally? That seems to be the most interesting thing. Maybe hard, but it's very interesting. Can you relate the conjecture that I told you to the AA conjecture? There are similarities that can be further investigated. Finally, is this kind of this sour conjecture? Is there a linear time attack for classical protocols with perfectly complete? It's a very independent. It's independent of everything, but I wanted to eventually put it somewhere. So these are all about quantum. The last one is not. And that is all I wanted to talk about. Thank you very much. And if there is a question, let me know.
Any other questions for anyone in the room? Okay, Mohammad, thank you so much.
Thank you, everyone.
Thank you for organizing.